Welcome to this next video in the playlist on topology. In this video, what we're going to do is discuss continuous functions between two topological spaces. Okay, so the structure for this video is we're going to start off by just reminding ourselves of firstly what a topological space is, and secondly what a function is. And then what we'll do is see the definition of a continuous function between two topological spaces and try and understand the intuition behind the definition of a continuous function. Okay, so firstly then, a reminder of what a topological space is. So topological space, fundamentally a topological space starts off its life as just a set. Okay, a set of arbitrary symbols, and I'll denote this like so. So this box is denoting the set which our topological space is going to start its life off as, and we'll denote the set capital X. So here is the set that's going to become our topological space. Okay, so it's just a set which has lots of symbols in. So these dots here, these will represent the elements of the set. Okay, and what we're going to do to turn this into a topological space, what we're going to try and do is define a notion of which points or which elements of the set are next to each other. So I want to define a notion of points being next to each other on this set, and that's what a topology is actually going to achieve. Okay, so intuitively, the informal intuition for what I'm going to do to define which points in this set are next to each other is I'm going to draw lines in between the points in this set and points that are next to them. Okay, so intuitively this is what I'm going to do. I'm going to have little lines in between points in the set that are going to be next to each other in the set. Okay, so that's intuitively what a topology is going to do for you. It's going to define which points in the set are next to which other points in the set. It's going to put a notion of connectedness to points on this set. Whereas before it was just a set of symbols, there was no notion of which points or which elements of the set were next to other elements. Whereas if we were to make a spider's web of lines like this, that would define that notion. Okay, however, the definition of a topology is far more subtle than that. As I say, this is the informal intuition for what we're going to do, okay, but this fundamentally isn't what a topology is. It informally can be viewed as being kind of like that. Okay, that's why I say it's the informal intuition for what a topology is going to do. Okay, but the formal definition of a topology is that the topology, which we'll call tau, is a subset of the power set of X. Now the power set of X is the set that contains all subsets of this set capital X. So you take every possible subset that you can possibly dream up of this set capital X, you stick those all into a set, and that's what is meant by the power set of the set capital X. So the topology is going to be a subset of this, and what that means is the topology is going to be a set containing elements which themselves are subsets of the set capital X. Okay, so a topology then is going to be a set of subsets of the set capital X. The topology of the set capital X will be a subset of the power set of X, a set of subsets of the set capital X. Okay, right. Now, in order for this set, tau, which is at the moment just a subset of the power set of X, to actually qualify for the title of being a topology, it has to fulfill three axioms. It has to obey three interesting properties which make it very, very interesting. Okay, and these three properties are that firstly, we insist that the empty set and the entire set X, which are both subsets of this set capital X, they have to be elements of the topology tau. So two subsets that you absolutely always have to have in your topology tau are the empty set and the entire set X. So that's property number one that we insist that tau must obey. Property number two that we insist tau must obey is that if you take any sets which are in the topology, and we call sets that are in the topology open sets, so you take U1 and U2, which are elements of the topology tau, it must be the case that if I intersect these two, so if I do U1 intersect U2, that is also an element of the topology tau. So this topology tau, this subset of the power set of X, it's a very clever subset of the power set of X, because if you have any two elements in that topology tau, it must be the case that if you intersect the two of them, you end up with another element that's in the topology tau. So you end up with another subset that is in the topology tau. Okay, so that's intersection, and the final axiom that we insist a topology must obey concerns the union of subsets of the set X which are in the topology. Okay, so we say that an arbitrary union of elements of the topology, so the union over alpha of loads of open sets in the topology U alpha, so all of these U alphas, they are elements of the topology tau. Okay, when we union together an arbitrary number of open sets from the topology tau, and understand this index alpha, it could be an finite index, it could be a countably infinite index, it could be an uncountably infinite index, it can be whatever you like, so you can union together an arbitrary number of open sets from the topology tau, and the answer, whatever you get, which will still be a subset of the set capital X, that must also be in tau. So tau, this subset of the power set of X, it has to be very well defined if it's going to obey these three properties. Okay, so if you do manage to come up with a subset of the power set of X which obeys those three properties, then you can call that a topology of the set capital X. And then if you associate that topology with the set capital X, then together the set X equipped with that topology is going to be called a topological space. So we've now elevated our set capital X up to a topological space. Now note, there is not just one topology that you can come up with for a set capital X, there are loads of them. Okay, so some trivial examples are, for instance, the chaotic topology, where the topology just contains the empty and the entire set. Okay, and also the discrete topology, where the topology is the entire power set of X, and you can verify that both of those topologies obey these three properties. Okay, right, so how then does this abstract definition relate back to our informal intuition of defining which elements of the set are going to be next to each other? Okay, how can we go from this abstract definition to drawing lines, or imagining that we can draw lines between elements of this set? Okay, well, the way that you can go from this set of subsets of the set capital X to a notion of which points are next to each other is that you can say that 2 points in this set capital X, so let's have a point A and a point B here, we can imagine drawing a line in between those two and saying that they're next to each other, they're very, very close to each other, if for every subset in the topology where one of these appears, so let's say A appears, B has to be in that subset as well. Okay, so if it's the case that whenever one of them appears, the other has to be with it, then we will connect them with a line, and we'll say they're next to each other. So let me say that again. In all of the subsets that are in your topology, if I'm going to draw a line between these two, it must be the case that these two elements of the set are together always. They're never on their own. You can never find one in a open set and then not have the other. Okay, so if they're both always together in the open sets in your topology, when they appear in the open sets in your topology, then I will draw a little line between the two and say that those two are next to each other, they're close to each other in this set. So that is the informal intuition behind how you can go from this subset of the set capital X, sorry, the subset of the power set of capital X, to actually having a notion of which elements in the set are next to each other. And as I say, that isn't fully rigorous. Okay, it makes sense for a finite set, it's perfectly doable for a finite set, but when you get onto infinite sets such as R2 and R3, it becomes more woolly and you have to start talking about infinitesimally close points. However, it is a very useful intuition, and I'm going to use this informal intuition to motivate our definition of a continuous function, and amazingly it does it very, very well. Okay, right. So now what I want to do is go on to the more meat of this video, because this is just a recap of topological spaces, and I should say that if you want to see this done in more detail, do watch my previous video in this playlist on topological spaces. Okay, so now let's start talking about continuous functions. Now before I talk about continuous functions between two topological spaces, let me just remind you of what is meant by a function between two sets. Okay, so functions then. A function is a mapping from one set, which we'll call capital X, to another set, capital Y, and at the moment these aren't topological spaces, they're just sets. Okay, so intuitively what this does is, let's draw the set capital X here, so this box will represent the set capital X, and let's draw the set capital Y over here. So here's X and here's Y, so let's add a bit of colour on here. So we'll have the set capital X coloured in red here, and we'll have the set capital Y coloured in orange here, and both of these sets are going to contain lots of elements. Okay, so I'll draw this on. So here we'll have these dots representing the elements of the set capital X here, and we'll have these dots representing the elements of capital Y here. So a mapping F is just going to take every element in this set here, and this set is called the domain of the function. So the starting set is called the domain, and the finished set is called the codomain. Okay, so this function will take all elements of the domain set, capital X, and it will map them onto an element in the codomain set, like so. So here's an example for this point here. So F will map this point onto this point over here. Now there are two important concepts that I want to make sure everyone is familiar with for functions. Okay, and those are the concepts of injectivity and surjective. Okay, so what is meant by an injective function firstly? Okay, so an injective function is a one-to-one function. So one-to-one is the more informal way of saying injective. And what it means for a function to be injective is that you never have more than one point in your domain being mapped onto the same point in the codomain. So I mean that you never have something like this. Okay, so if it was the case that our function f mapped this other point in the domain also onto that same point in the codomain, then this function would be non-injective. Okay, now it's perfectly reasonable that a function can map two elements of the domain onto the same element in the codomain. Okay, we don't insist that all functions have to be injective. The definition of an injective function is one where this never happens. Okay, so where every different element in the domain is mapped onto a different element in the codomain. So as soon as I've defined this portion of the function, I can instantly conclude that my function is not injective. Okay, so injective means that one element here goes to one element here, not many elements from here going to one element here. So this would be a many-to-one function because multiple elements in the domain are being mapped onto the same element in the codomain. Okay, right, so that is the concept of injectivity, and then there's another big fancy word for functions, which is surjectivity, and all of this is perfectly well defined in set theory. We don't need any topology to do this. So a surjective function is an onto function. Okay, so the colloquial word for surjective is onto. And a surjective function is one where absolutely every element in the codomain has at least one element in the domain being mapped onto it. So if I just finish this function up, let's say this one goes here, this one goes here, this one goes here, where should I have this one going to? Have this one going here, and it's worked perfectly, who would have thought it? And this one can go here. And you can see here that one point here has not got anything being mapped onto it. We've now sent every element in the domain to an element in the codomain, and just one element, actually no, there's another dot there, but never mind. Okay, two elements then. There are two elements here in my codomain which don't have anything being mapped onto them from the domain. Okay, so this is a non-surjective map, because it's not onto. It's not the case that every single element in the codomain has an element in the domain being mapped onto it. Now I should say, what I've drawn here is a perfectly reasonable function. It's taking all the elements of the domain and mapping them onto elements in the codomain. Okay, it's perfectly reasonable, but it satisfies neither of these two fancy words. It is not injective because we've got this point here, which is the image of both of these points here in the codomain, and it's not surjective because we've got points in the codomain which have nothing being mapped onto them from the domain. Okay, so this map doesn't satisfy either of these two criteria. So I hope these two words are clear. Now, if a mapping obeys both of these, if it's both one-to-one injective and onto surjective, then we call it bijective. So I hope these concepts are familiar from set theory. Okay, right. So now let's go on to the notion of a continuous function. Now, in set theory, it means absolutely nothing to say that this function is continuous. It's not defined. You can't define it just from set theory. Okay, if we've just got one set as our domain and one set as our codomain, it is meaningless to speak of whether this function is continuous or not. You don't have enough structure to define what is meant by a continuous function. Okay, you need these structures here, at the very least, to be topological spaces in order to talk about what it means for this function to be continuous. Okay, so now what I'm going to do is I'm going to give the definition of a continuous function and then try and give the intuition behind why the definition is the way it is. Okay, so what we're now going to do then is we're going to elevate these two sets, the domain and the codomain, up from being sets to being topological spaces. So I'm going to turn my set X into a topological space. I'm going to equip it with some topology which I'll call tau X, like so. And I'm going to elevate Y up as well to make it a topological space by equipping it with a topology tau Y. Okay, now it's very important that you understand that whether a function is continuous or not between two sets which have got topologies on them, so two topological spaces, is completely and utterly dependent on which topologies you pick to equip these sets with. Okay, so we might conclude that this function, capital F, between the set X and Y with these two topologies is continuous, but if you change the topologies, even if the function between the two sets remains absolutely the same, it might destroy continuity. Okay, so it's completely and utterly determined by the topologies that you put on these two sets. And of course we know that a set can emit many different topologies. Okay, right, so what does it mean then for F to be continuous? So what is the definition? F is continuous with respect to these two topologies, you should say. Okay, so in full you would put with respect to the topology tau X on X and the topology tau Y on Y. Okay, so what then is going to be the definition of this? This function is going to be continuous if all of the open sets in the codomain here, if their pre-image in the domain over here, the domain topological space, is an open set. Okay, so here is going to be the definition. For all open sets in the topology of Y, so I'll call open sets in the topology of Y by V. So for all V is an element of tau Y, okay, so V is going to be some subset of the set capital Y, and it's going to be an open subset that's in the topology tau Y. Okay, so you pick any element you like of the topology tau Y, and I might just actually draw another picture for this. So I'm going to actually denote my set capital X and my set capital Y by boxes here, okay, and we'll have both of these equipped with a topology tau X in the case of X and tau Y in the case of Y. So just hold on a second whilst I colour these in. So here is my set capital Y now with a topology on it, and here is my set capital X also with a topology on it. Okay, so now what am I doing? I am taking some subset of my set capital Y, which is an open subset, so it's going to be in the topology tau Y. Okay, so I take any subset of the set capital Y that's in the topology tau Y. It must be the case that the pre-image, which I will notate F inverse of V, and I'll just remind you exactly what that means. This is called the pre-image of the subset capital V, which is a subset of capital Y. And what this means is all the elements in the set capital X, I'll say all little x is an element of capital X, such that little x is going to be mapped into this subset capital Y by the function f. So f of little x needs to be an element of this subset capital V. Sorry, I said capital Y previously. The subset capital V. Okay? So, intuitively then, what does this mean? The pre-image is going to be a subset of our set capital X over here. Okay, so I'll draw it here. So here, this is the pre-image of the subset capital V. And again, the concept of the pre-image is a concept from set theory. You don't need topology in order to define the concept of the pre-image. It's something that's defined in set theory. So I'll denote this pre-image in yellow here. Okay, and it's going to be the subset that contains all points, little x, such that when I take f of little x, so I act the function f on little x, the answer ends up inside my original set, capital V, which is a subset of capital Y. Okay, so the pre-image of a subset in the codomain is just all the elements in the domain which are mapped into that subset of the codomain by the function. So it's a subset of the domain which is mapped onto that subset in the codomain. Okay, so what about the pre-image? I've just defined the pre-image, but I haven't actually said what I want to be true about it. So the pre-image of the subset V must be an open set according to the topology on X. So this subset here must be in the topology of X. Okay, and that's it. That is the definition of a continuous function between two topological spaces. Okay, it's just a function for which all the open sets in the codomain, their pre-images in the domain are also open sets. So the pre-image of an open set must be an open set, and if that's the case, then we call this function, little f here, a continuous function. Okay, so that's the abstract definition of a continuous function. I think what we'll do now is have a break. You can sort of try and absorb this definition, and then what we'll do is I will try to give you an explanation as to why this is the definition of a continuous function, using my informal intuition about what a topological space truly is representing.